In this video, we're going to talk through how to recognize even and odd functions and how to do the algebraic tests to prove that a function is even or odd. So let's just do a quick overview of what even and odd functions are. So we call a function even when this statement is true. F of negative x is equal to f of x. And this is going to be true for all values of x. So really what that means is that the graph is going to be symmetric with the y-axis. So if you look at the picture of the graph here on the left, or this would be the right, this parabola is symmetric with the y-axis, so it cuts it perfectly in half and there's mirror images on both sides. The reason why we call functions that do that even is because all the functions x squared, x to the fourth, x to the sixth, basically all of your even powered functions are going to be symmetric with your y-axis before there's any transformations that occur to them. So most of the functions that have those powers are going to be even. Obviously there's going to be some special cases here and there, but it's not just those functions that have symmetric with your y-axis. The graph of cosine, which we'll talk about later in this class, the graph of cosine is also symmetric with the y-axis. So this is also an even function. So if you look here, we have the same thing on the left side of the y-axis as we do on the right side of the y-axis, and that's true for all of those points. So let's go ahead and take a look at what an odd function is. We call a function odd when this statement is true. F of negative x is equal to negative f of x. And that's also going to be true for all values of x. Essentially what that means is that the graph is going to have symmetry to the origin, which is, I kind of like to think of symmetry to the origin more as like a rotational symmetry, where if you picture the origin as being your pivot point, so if you look at this graph here on the right, if you imagine that as your pivot point, if you take what happens, say for example, in the fourth quadrant, this little piece down here. I mean, granted, it's going to be true for the whole graph, but sometimes if you just kind of isolate a little piece of it, it makes it a little bit easier. So imagine if you take that little piece of that graph in the fourth quadrant and you rotate it 180 degrees, it's going to give you this piece of the graph that's in the second quadrant. So basically when you look for symmetry to the origin, you're looking at your second and fourth quadrants. If what you have in one of those quadrants will rotate 180 degrees and give you what's in the opposite quadrant. You can also look in the first and the third quadrant, like this graph shows, for the same thing. So again, these functions got their odd name because all of the odd parent functions, x cubed, x to the fifth, are all going to be have symmetry to the origin. Again, it's not just those polynomials that have the odd name. There's also graphs like the graph of sine. So if you look at the graph of sine, we just isolate that one little piece, rotate it 180 degrees, you're going to get that piece down here. So that's also an odd function. Again, not every function has to be even or odd. In fact, most functions are generally neither. Because if you remember, we have all of our parent functions, but then we can do transformations, and really an infinite amount of transformations to all of the parent functions. So sometimes when you start introducing some of the transformations, then the graphs no longer remain even or odd. So again, there's just names, even and odd, they're just names, and it has to do with how are they symmetric. So a lot of times you can just look at a graph and kind of get an idea of whether the graph is going to have symmetry with your y-axis, so if it's even, or symmetry to your origin, so it's odd. But looking at the graph's not really a proof of the function being symmetric, and that's where these algebraic tests come into play. So to determine whether a function's even, odd, or neither, we have to prove those couple statements, the statements that f of negative x equals f of x for the even function, or we have to prove that f of negative x equals negative f of x for the odd functions. And it seems kind of complicated, but really when you look at it, it's a pretty simple test. So I kind of devised this little graphic organizer to help you out. So to test any function to see whether it's even, odd, or neither, what you're going to do first is you're going to take your original function and you're going to substitute in a negative x everywhere you see an x in that function. You're going to simplify it. So usually that involves raising it to some power and then seeing kind of what happens to the signs of that variable. And then we're going to do two things. You're going to, over here in this top right box, you're just going to write the original function. If what you get over here, after you plug in negative x, so if what you get over here matches what the original function is, if those match, then we call that function even. If after you plug in negative x here, if over here, after you're going to take the original function and you're going to multiply it by -1 and then simplify it. If what you got here matches here, then we're going to call that function odd. If it doesn't match either of those, then it's neither. So let's take a look at a few examples. Alright, so here we have f of x is equal to -5x divided by the absolute value of x. This function doesn't match any of our parent functions, so unless we were to graph it, we really don't know whether this function is going to be even or odd. So the first thing we're going to do is we're going to plug in negative x in the original equation, and I would plug this in parentheses. So we have -5 times negative x in the numerator, and the denominator we have absolute value of negative x. Now I'm not going to put a parenthesis in the absolute value because that's the only thing that's happening in the absolute value, so I'm just going to leave that as it is. So if you look at this, up top, now we're going to simplify. So I just plugged in negative x everywhere there was a x in the original function. Now we simplify. Up top, we have -5 times negative x is going to give us a positive 5x. And in the denominator, anytime you take the absolute value of a negative number, it's still going to leave you with a positive x. So this is what we're going to compare what's in these two boxes to. So for this first one, I'm just going to recopy the original function. So it's -5x over absolute value of x. And just do a quick compare. Does this function match this function? No. If you look at the numerator, the one on the left is positive. This one on the right is negative. So this shows that it's not even. So it's not going to be symmetric with your y-axis. So down here, you're going to take and multiply the original function by 1, or -1 rather. So there's your original function, -5x over the absolute value of x. There's our -1 out front. Now just be careful with this. Multiplying in by -1 seems really simple, and it is, but you just have to make sure that with the fractions, you don't take that -1 and multiply it by everything in the fraction. Think of -1 on the outside as a -1 over 1. So really when you multiply in a -1 on a fraction, it's just going to change the numerator. And the denominator, when you multiply those together, is not going to change. So over here we have absolute value of x. And up top, -1 times the -5x gives us a positive 5x. Alright, so now we got to take this, compare it to here, and those are a match. Hooray! So the conclusion is the original function is odd. And if you would you can go ahead and graph it and look at it in your graphing calculator and see if you can kind of picture that rotational symmetry around the origin. But you're not always going to have your graphing calculator to help you out, but if you just do this quick check, it will show you whether it's even or odd. Let's do one more. Alright, here we have f of x is equal to the cube root of 7x squared plus 5. And if you look at the powers that you have in there, like inside the radical, you have a 7x squared plus 5. So if you're just kind of looking at that, you might think this graph is even. But with that cube root on the outside, I'm not really sure. Because the cube root of x, if you remember that parent function, it looks like this. And that's an odd function. So I'm not really sure how this one's going to turn out. So let's just go ahead and do the test to see. Alright, so first things first, I'm going to plug in -x, where there was an x in the original function. Again, watch, put it in parentheses. And then we have to simplify it. When you simplify it, you're really just looking at what's going to happen here. So if you take any negative number and you square it, it's going to give you a positive number. So really we have 7 times positive x squared plus 5, cube root of that. Simplify it a little bit more, take out that multiplication sign. So we have cube root of 7x squared plus 5. Alright, so this is what we're going to be comparing. So if I go over here and just recopy the original function, cube root of 7x squared plus 5. And now we're going to look at these two together. Oh, would you look at that? They match. So this graph is actually even. And just to show you how the odd test isn't going to give us it's not going to give us a match. If I take a negative and I multiply it in by the original function, well, I guess that's really all you can do. With the radical, you can't take and distribute this negative underneath the radical. That cube root and the radical sign prevents that. So really, this just simplifies to negative cube root of 7x squared plus 5. And since these two are not a match, it's not odd. So that's how you do the test for even and odd. I will do another video to show kind of a couple more examples that are from a review sheet. So you can just see a few more just to kind of help you out.
Made with Doodlecast Pro.